Now we have to find the integrated rate equation for the first order reaction. We have taken the reaction where reactant gives the product and the rate of the reaction, that is the differential rate of equation, is minus rate of change of concentration of the reactant, and that is equal to rate constant multiplied by the concentration of the reactant raised to the power order of the reaction. This is the x is the order. And for first order reaction, x is equal to 1. So substituting the value of x equal to 1, we will have rate minus dr by dt, that is equal to k into r. This implies that dr by r equal to minus k dt. On integrating, we will have ln r, it is with base e, and it will be equal to minus kt plus c. This is our equation number 1. To find the constant of integration, that is c, we use initial condition that at time t equal to 0, concentration is R0. And substituting this value, we will have ln R0 equal to minus k into time is 0, so it is plus c. Or we can write c is equal to ln R0. And substituting this value of c in the first equation, we will have ln R equal to minus kt plus ln R naught. This is our equation number 2. This equation is the equation of a straight line. If we compare this equation number 2 with the equation of line, that is y equal to mx plus c, then slope of the line will be equal to minus k and intercept will be ln R0 on the ln R axis, that is y axis. So if we draw the graph between the time on the x axis and ln R on the y axis, then the intercept on the y axis will be at a point with value ln R0, and this is having the negative slope. Slope is equal to minus k. Further manipulating the equation number 2, we will have ln R0 minus ln R equal to kt. This implies that ln concentration of R0 divided by R, that is equal to kt. If we draw the graph between time and ln R0 by R, again this is the equation of a straight line. Comparing with the standard equation of the straight line, that is y equal to mx plus c, we will see that slope of the line will be equal to k and intercept is 0. That means line passes through the origin. So graph will be a inclined line passing through the origin. Further manipulating the above equation, that is ln R0 by R equal to kt, we can find the rate constant k, that is equal to ln R0 by R divided by time. And converting the base of the log from e to 10, this will become 2.303 by t log R0 by R. Now we have to find the half-life. That means t equal to t1 by 2, the concentration of the reactant becomes half of the concentration at time t equal to 0. So using the equation number 4, we will have k equal to 2.303 by T half. This is the half-life into log, and R0 is the initial concentration, and concentration at time T 1 by 2 is R0 by 2. This will be equal to 2.303 by T half into log 2, and value of log 2 is 0.3010. So this implies that K is equal to 0.693 by T half, or T half, that is a half-life, will be equal to 0.693 divided by the rate constant of the first order reaction. Here we see that half-life is independent of the concentration of reactant in case of first order reaction. Further, using the equation number 4, that is K equal to 2.303 by T into log R0 by R, we can derive an important relation between the T75% and T50%. T75% is the time duration in which 75% of the reactant becomes disappeared. Similarly, T50% refers the time period in which the 50% of the reactant becomes disappeared. So if we take the T75, then because rate constant will be same, it will be 2.303 divided by T75% into log. Initial concentration is taken R0, and the remaining concentration for 75% disappearance, then remaining concentration will be 25%, that is equal to R0 by 4. So we replace here R0 by 4. Therefore, the K will be equal to 2.303 by T75% into log 4. Similarly, for 50%, rate constant will be equal to 2.303 by T 50% into log concentration is R0 initially, and after 50%, remaining concentration will be R0 by 2. So it will be equal to 2.303 by T 50% into log 2. Now, comparing the equation, left hand side has the value K, because K is same for the reaction. This implies that right hand side must also equal, or we can write 2.303 by T75 degree into log 4. Log 4 can be written as 2 into log 2. 4 can be written as 2 raised to power 2, and power becomes out of the log, we can write it as 2 log 2. And it will be equal to 2.303 by T 50% into log 2. So cancelling the common term, 2.303 get cancelled, log 2 get cancelled. So we have T 50%, 2 into T 50% will be equal to T 75%. So this is an important relation we have to remember. Now again, using the equation number 2, which is ln R equal to minus KT plus ln R0. Rearranging the term, we will have ln R minus ln R0 equal to minus KT, or it is ln R by R0 equal to minus KT. We can write it as R by R0. This will be equal to, because base is E, so we can write it as exponential power minus KT. So concentration R at time T will be equal to the initial concentration multiplied by minus KT. Now suppose this time period T, after which the concentration of the reactants is R, it comprises the n number of the half-lives. So replacing the value of T with the value n into T half, we will have concentration R will be equal to R0 e की power minus k into n into t 1 by 2. Also, so replacing the value, we will have R will be equal to R0 into e raised to power minus k into n into ln 2 by k. K and k get cancelled, so it can be written as R0 e raised to the power minus n into ln 2, or R0 e raised to the power ln 2 raised to power minus n. And this term will simply becomes R0 into 2 raised to power minus n. Therefore, concentration after time t will be equal to initial concentration into 1 by 2 raised to power n.